Okay. Thanks everybody for joining. This is a webinar that we are going to talk about the Oyster Aquaculture Nitrogen Removal Calculator developed by NOAA's Northeast Fisheries Science Center. We have the team that developed the calculator here. We're going to do a demonstration and we are going to do some interactive audience participation and Q&A. So Ryan, go ahead.
Hey, Julie, you ready?
Yeah, well, actually, the first slide is just the
We're still
overview.
seeing the first slide, yeah.
Oh,
There we go.
There we go. So we're going to give some background, data aggregation and analysis of how we came up with the tool. We're going to demonstrate the tool, as I said. We're going to show how a report is generated from the tool. And then we're going to talk about a potential use case by an independent company. And we're going to do some feedback through an interactive platform. And then we'll have a Q&A at the end. So I will hand it over to Julie Rose, who led the data collection for this tool. So go ahead, Julie.
Thanks so much, Zach. So I wanted to talk to you folks today. First off, I wanted to give a little bit of background about excess nutrients and why removal of excess nutrients is considered an environmental benefit. So the problem with nutrients, and specifically nitrogen, which is what this calculator is focused on, is not that nitrogen itself is harmful or toxic to life in general. So nitrogen is actually a building block for all life. Everything from the smallest microbe up to fish and even people require nitrogen to live and to grow. The problem with nitrogen comes when it is in excess, when there's too much nitrogen. So what has happened is as coastal populations have increased, large amounts of nitrogen are getting washed into our waterways. And once in these waterways in excess, this can lead to problems like algal blooms, loss of seagrass habitat, and fish kills. Now, unfortunately, on the US East Coast, a large number of estuaries and coastal environments have this condition of excess nitrogen, which scientists also call eutrophication, and so are experiencing some of these environmental problems. And in these locations, there are nitrogen management programs in place that seek to reduce nitrogen in order to alleviate these environmental problems. So you go to the next slide. So shellfish can help reduce nitrogen, and there are three mechanisms by which shellfish can accomplish this. Thought it was important to go over this because I need to be clear that our calculator is really only considers the first of these pathways. So the three pathways are assimilation of nitrogen into tissue and shell of oysters and other shellfish as they grow. The second pathway is through enhancing a naturally occurring process that converts organic matter to dinitrogen gas. And the third mechanism is simply burial in seafloor sediments. So we really only have focused on assimilation into tissue and shell for our calculator. And the reason for this is twofold. First, there's really great literature supporting this process in the scientific literature. And the second reason is that several locations on the US East Coast, several nitrogen management programs have approved the use of shellfish aquaculture assimilation into tissue and shell as a nutrient best management practice. So if you could go to the next slide. And so one of the places where nitrogen management program has approved the use of shellfish aquaculture for nutrient removal is Chesapeake Bay. And EPA has approved an estuary scale approach. They convened an expert panel that identified two key metrics that are needed in order to make a confident prediction of nitrogen contained within an individual oyster. And so these are shown here. The lower left-hand corner, we have nitrogen concentration. So this is the percent of nitrogen in an individual animal's tissue and shell. This metric exhibits low variability in the literature. And because of the observed low variability within the Chesapeake Bay, the panel made the recommendation to use simply a single value bay-wide. On the lower right-hand corner, you can see the second metric is oyster morphometrics. And so specifically, this is the relationship between the size of an oyster, its shell height, and the dry weight of that animal. And this metric exhibits a lot more variability. And for this reason, the panel aggregated a lot more data in order to be confident that they they are accurately capturing a good middle value, a good typical value for this relationship between animal size and weight bay-wide. And if you're interested, I have a link to the EPA report that goes into a lot more detail about this in the top right-hand corner. So if you want to keep going, next slide. Okay, great. So what we've done is take this approach that was approved by EPA in Chesapeake Bay and extend it to the regional scale. So we worked very closely with some extremely generous researchers across the region whose logos I have shown here, who were able to provide us with data that they collected from North Carolina to Maine. So what we were trying to do in our data aggregation effort is really prioritize farm data. So we first looked across all the states for data that we could find that was collected on working shellfish farms. If that was not available, we went to a second tier of data, which is data collected by researchers who are emulating farming practices. And in, I think, just one state where that type of data was not available, we collected data from wild oysters that were grown within water bodies that had working farms. So the results of our aggregation effort were that we have 1,500 samples for oyster tissue nitrogen concentration, 500 for oyster shell nitrogen concentration. And again, those are the two low variability metrics. On the high variability side, we have a lot more data, 5,500 measurements for tissue and 2,000 measurements for shell. And if you're interested, we have archived our data and made it publicly available. Please feel free to go take a look and download it for yourself. I have a link in the top right-hand corner. Next slide. So I'll give you a very high-level overview of the analysis that we did that underpins the calculator. If you want the details, I'd encourage you to go to our publication, which I have linked in the top right-hand corner. We made this open access. It's available from a peer-reviewed journal, PLOS One. So please feel free to download it and check out if you'd like more information. What we did see was consistent with what the Chesapeake Bay expert panel reported. There's low variability across our data set in terms of both tissue and shell nitrogen concentration. And I have the data plotted here. This was true when we split the data out by state, when we looked across 3 common types of cultivation practices across the Northeast region, and when we looked at both diploid and triploid oysters. So this low variability, both in tissue and shell nitrogen, led us to be comfortable applying a single average concentration region-wide, which is 7.7% for tissue and 0.19% for shell. Next slide. So similar to what was observed within the Chesapeake Bay, we did see much higher variability associated with this relationship between animal size and animal dry weight. But we feel fairly confident that we have collected sufficient data to really adequately capture this variability in this relationship across the region. So we've on the left-hand side, you can see there's a map here with our sample locations spread from North Carolina all the way up to Maine. On the right, I have the data plotted here with, again, the animal size on the x-axis and the weight on the y-axis. And what we have, the purple line that runs through it is the median or the average, the middle value, what we think is a typical value for this relationship between size and dry weight. We also split up our data set and we looked at how this relationship varies across ploidy, across cultivation practices, and when we compared New England oysters to mid-Atlantic oysters, and we saw really very small differences in this relationship when we looked at these potential influencing factors. And for this reason, we again feel fairly confident in taking a simple extension of the Chesapeake Bay approach and applying it to our region-wide data set. The other thing that we did, if you can go forward one more slide, Ryan, is we actually compared our data set to the Chesapeake Bay data set. And so so what I have plotted here is our data that is, again, from North Carolina to Maine, shown in the dark gray, and then the Chesapeake Bay program data that was analyzed shown in the turquoise blue. And we were really pleased to see that the variability that was observed within a single really well sampled estuary, just within the Chesapeake Bay, is very similar to the variability that we saw across the whole region. This what we think is going on here is that we're actually have sufficient data that we're starting to potentially capture the physiological limitations of this relationship. And it gives us confidence in a median regression being a good predictor of animal weight. So because the variation in nitrogen concentration was so low and we have such a great data set, or such a great data set representing the morphometrics metric, the calculations that underpin the calculator are really actually quite simple. And Ryan is going to go now into a demonstration of the calculator and how it can be used.
All right, thank you for that, Julie. So really the impetus for this calculator was based on feedback from resource managers who were interested in easy to use tools that produce location and operation appropriate values for these ecosystem services. So that's what we set out to do, build a simple tool based on robust data. It's all based on open source work. We have links throughout the calculator itself to all of the data, to the manuscripts that describe the process, and we've been trying to be as transparent and open as possible throughout this process. So here's a link, and did we get this in the chat already?
Yep, I just put it in the chat.
So there's a link there at the top. You can use the screenshot to get to the calculator as well. And then this is just what it looks like here. So I'm going to X out of this real quick. And
so Ryan, let me just jump in real quick. For those that cannot see the shared screen, Ryan's going to demonstrate some use of the tool, but if you go to the link in the chat, you can kind of follow along, even if you can't see the screen.
All right, so we're very interested in getting feedback on this, and as part of that, we're trying to basically be on top of anything that we can do to improve the tool. So I'm giving you here a preview of the tool that's been based on some feedback that we've already had. So this is a little preview. This is not the live calculator that you'd go to currently. So it's just got one little extra tweak. So when you first open the page, you get 3 tabs across the top. You'll notice there's a calculator version. So we have version control. This is all based on GitHub open source software. The calculator tab is the one that you're going to want to use to actually run through the actual process. But I'm going to talk about these other 2 first. So first, there's a reverse calculator, and this just basically allows you to estimate the number of oysters that are required to offset a nitrogen load. So I'll just type in 1,000 pounds of nitrogen, and you're selecting a size. It's defaulting to 3 inches for oysters. And you can see right here, it's saying that you need 3,210,000 oysters harvested to offset a nitrogen load of 1,000 pounds. So that was just a quick little demonstration of that aspect there. And that was something that we sort of just threw in as maybe an educational tool, something that you can just kind of play around with to see, the effect of oysters on the nitrogen. So on the About tab, this is where, and just as a general FYI, these big blue boxes have like the instructions for the tools and all the pertinent information that you're going to want to see. But this one lays out at the very start the 2 inputs that really have the effect on the calculation. So that's the number of oysters harvested and the size of the oysters at harvest. That's really the predominant factor on this calculation. And then there's a little bit of background on the research itself, an infographic that we had created that sort of demonstrates the general process of oysters removing plankton that take up the nitrogen as runoff. So that was a nice bit of outreach that we did. There's a map, an interactive map. You can see where the samples came from that underpin the study. And we have links to the data itself throughout this this About tab. There's the project team. Most importantly, here's a comment box that email address that you can reach us at if you have any questions, any comments, suggestions. Please use it. We are responsive and we take it very seriously. Then there's references and a disclaimer at the bottom. And let's see, we'll jump right into the calculator tab. And I'll just step through a general quick use of the tool itself. So again, there's the important information in the blue box here. You can read that. But basically it's saying there's three steps. So there's farm practices, there's farm location, and then there's harvest details. Those are the three things that you're going to want to fill out. So farm practices is just the name of the farm. So this is incorporated into the report at the end of the demonstration. And you can select the culture method that were used to grow the oysters. So off bottom, on bottom, that would be essentially if you didn't use any gear as well, you could select on bottom, or you could select multiple methods. And again, these don't actually influence the calculation. It's just part of the reporting. It's something that we like to keep track of as well. And then there's oyster ploidy, diploid, triploid, or combination. Again, not influencing the calculation. Farm location. This is just coming up in the report. And then an approximate coordination. So you can zoom in to wherever you are, select the drop-down pin, put it there. And the latitude and longitude are recorded. And then this is also sent with the information in the PDF report that you can submit. So then we get down to the harvest details. This is where you're actually going to have influence over the calculation. So it's defaulting to a size of 3 inches. This is in inches. The range is currently set between 2 and 5. That was based on a consensus that we sort of figured was going to be most common. We've already had a comment that some people are interested in using seed oysters and would like to know the nutrient contribution from removing seed oysters. So that's something we're taking into consideration at the moment. And then you just enter the number of oysters at harvest. You can select the date range over which those oysters were harvested. That's just something that's going to go into the report as well. You can choose your output units, kilograms or pounds. And it will tell you how many pounds of nitrogen your harvest has contributed to. And then this is just a little bit of addition that we added to the current calculator. So we have an equivalent bags of fertilizer. That was just based on some feedback that we had. So to get the report, you just click on Generate PDF Report. You're not going to see it, but it's showing up on my other screen. Oh, yep, there you go. So save the report, and then you can then use that to submit along with your permit applications. And with that, I'll turn it over to Chris.
Okay, so thanks everybody. My general role in this project was to help connect with the management community and understand how we might take this tool and best develop it so that the outputs would be able to be integrated either into a permit application document or into their review process. So we reviewed a number of the regulatory processes, largely across 3 New England states, and then with the Army Corps of Engineers and NOAA. And what we identified was, generally speaking, every project is going to go through some level of Army Corps of Engineers review under their Section 10 of the Rivers and Harbors Act. And Section 10 is what they call a public interest review process, where there's a number of factors that the Army Corps project manager or permit reviewer is going to look at and, see where this project's going to have effects, whether they're negligible, beneficial, adverse, neutral. The idea is to take a look across. As we probably all know, at least those that have been through the permit process, it's a lot easier to calculate the potential adverse effects than it is to calculate the potential beneficial effects. But the public interest review process charges them to do that. And they're either going to do that every 5 years when they review the general permits or state permits that most of the growers are permitted under, or they're going to do it when they're doing an individual permit review process for a larger farm or a place where there is no public interest review or general permits or nationwide permits in place. As we looked across these public interest review factors, water quality is a clear place where the positive effects of shellfish oyster aquaculture would play into their review process. And where we did see examples of the Army Corps of permit managers or project managers documenting use, they used very generic text without any kind of quantitative assessment. So what we heard was, provide us a very easy to use text description of the positive effects that might come from nutrient removal, as well as a solid peer-reviewed value that we could feel comfortable integrating into the permit application document. And that's largely what you see. You're going to get this table as well as a summary text. It's very succinct, short text that's project specific and includes the ecosystem value of this work. And then it also references the federal regulatory nexus. This is also relevant in the essential fish habitat consultation, as well as other reviews, possibly if we're dealing with water quality as it relates to protected species. What we did note, and I'll just briefly mention this, is that there's a number of other factors that eventually we'd love to incorporate into a calculator, such as economics and an economic multiplier, habitat provisioning, and fish and wildlife services that all have some documentation, and slowly we're working towards quantification of those services that could then be generated. All right, back to you all.
All right, we are gonna now change gears, and Chip Terry is gonna talk about how he might incorporate this tool into a product that he provides. And Ryan, if you stop your share, Chip should be able to share his screen. All right. We are seeing that, Chip. If you want to just enter present mode, then go right ahead. Hey, Chip, you're on mute right now.
Can you hear me now?
Yes, we can hear you now. Thank you.
You missed all of my thank you to you guys, and the fact that I'm not a scientist or a regulator, but I'll jump right in. So Blue Trace, we started as a company that focused on shellfish aquaculture and particularly regulatory compliance, particularly around shellfish tagging and logging. So this is a really natural fit to what we do. We do a lot of different things now, but particularly around the tagging and label and the digital logging, we think this is a great addition. Because today we have about 528 different clients, some producers and a lot of producers and some distributors. Collectively, this group has printed over 8.4 million tags, which is a ton of tags. You can stretch it all the way from Maine to South Carolina. And so we took a look at this and said, well, what would happen if we actually use this calculator within our system? So last week, our clients printed over 71,000 tags, which equates to roughly 7.1 million oysters harvested just last week. Using the calculator, that's about 2,270 pounds of nitrogen removed from the water systems just in the last week. And then we just did a brief calculation of how many, if you fertilize your lawn at the average of 2 pounds per year per square foot, it's 1.1 million square feet of lawn. We think this could actually be really neat for like your normal, just talking to your neighbors, like here's how much you're actually using. It's a pretty easy calculation. It can be put into a spreadsheet very easily. We'll certainly think about incorporating it into our platform going forward, but anybody can use that calculator now. Because Honestly, I look at this as an incredible triple win. And this is just one more thing in the larger benefits of shellfish aquaculture. Obviously, it's great for our health. The New York Times, if you guys haven't read this recent article in the New York Times, basically it's singing all the praises about shellfish. It's great for our communities, and communities like where I grew up in Maine, where people are actually, raising family and sending them to college on oyster farms. That's awesome. And it's great for our environment. Certainly low carbon emissions. If you look at a protein source with low carbon emissions, you almost don't get better than shellfish aquaculture. And now nitrogen removal. So I think there's huge benefits that this whole community can do. And I applaud NOAA for coming out with this calculator on this. So always happy to have a refer us. This is the sales pitch, but I'd love to talk to anybody that is interested in learning more about Blue Trace. But again, thank you for inviting me here.